Alright, so in this video we're going to introduce the concept of internal forces that develop within structures. So our goal for this lecture is to determine the internal forces within a structure, Alright, the reason we're interested in doing this is if we know the internal forces within each component, we may properly design each component to prevent failure. Alright. So for example, if we have a cantilever beam that's drawn here, and we have it's fixed at one end at point A, and there's two applied loads, P1 and P2. Alright, and we want to determine what is the internal forces within the member at point B. So to determine that, what we're going to do is we're going to draw a free body diagram of our system. Alright, so on one end we have our fixed connection. Alright, so we know that at a fixed connection, a fixed connection will create supporting reactions. So for a 2D system, we know that a fixed support will apply a moment. It can apply a force in the x direction, and it can apply a force in the y direction. So those are our supporting. So we also know that we know at the other end of our system we have our two applied forces. We have P1 and we have P2. Alright, so we wanted to draw a section. What we're going to do is determine the internal forces at point B, which we're going to draw a section cut. So we're going to split our system into two parts. Alright, so at this side here, this is point B, and at this side here, this is also point B. So we've cut the beam into two parts. Alright, so to make sure that we have the same type of loading situation that we drew on the left-hand side, we have to include the internal forces at point B on both the left-hand side and the right-hand side of our section cut. Right? So on the right, so what we're going to do is we're going to draw there's going to be three internal forces that are going to be caused by the two applied loads. Alright, we're going to have our normal force, NB. Alright, we're going to have our shear force, which is going to be VB. And we're going to have a couple moment, MB. Alright, and then on the left hand side of the diagram we're going to have equal and opposite forces. So we'll have NB again. Alright, we will have V of B, and we will have M of B. Alright, so again, N of B is the normal force, or the normal internal force. VB is the internal shear force. And MB is the internal couple moment. It's also often labeled as a bending moment. Right. So if you hear the word internal bending moment, it means the internal couple moment. So you may use either the left hand side or the right hand side to determine the internal forces, left hand side or right hand side of the free body diagram. So if you summed all the forces in the x direction and set that equal to 0, you could determine NB. If you summed all the forces in the y direction and set them equal to 0, from that you could determine VB. Alright, and then if you summed all the moments about point B and set that equal to 0, from that you could determine the internal moment B. Alright. 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 So one thing I should point out is that all of these forces and moments will act at the center or the centroid of the structure or of the body. So in 2D, we'll draw our internal forces like this. Alright, and then for 3D cases, what we're going to have, alright, is we should have, if we draw our coordinate system out, alright, we'll end up getting, we'll have 6 internal forces. We'll have we'll have about the y-axis, we'll have our normal force, which we call Ny. We would have about our z-axis, we would have our shear force, which we would call Vz. And then about our x-axis, we would have our shear force Vx. Alright, and then we would have 3 couple moments about this system as well. We would have our moment about y, we would have our moment about x, and we would have our moment about z. Alright, so sometimes the moment about the y-axis is the length of a beam or a structure. Sometimes that's labeled as the torque that's going along the structure, but the torque and the moment about the y-axis are the same. But I guess the main thing to keep in mind is that if you have a 3D problem, you need to include all 6 internal forces, not just the 3 that we've drawn in 2 dimensions. Right. So before we do some examples, we just want to go over some of the sign conventions for what is considered a positive and a negative normal force, shear force, and moment. So for internal forces, so for a normal force, if we have a structure, we have tension being applied on both sides of our structure, and we did a section cut through the center, what we'd end up getting is we'd have our normal force coming out of our section cut. Alright, so any normal force is considered a positive if it creates tension at the internal surface. Alright, so for a shear force, we have, if you had a structure that had two external forces like that, we took a section cut through the center, we'd end up getting oops, let me redraw that, sorry. Draw these forces the other way. Alright, so we had two forces equal and opposite being applied on the other opposite sides of the section cut. What we'd end up getting is where you get two shear forces, one on each side, and then we'd have our external forces still here. Alright, so a shearing force is considered to be positive is that if it would create a clockwise rotation of the part. So in both of these cases, our shear force would cause both of these parts to rotate in a clockwise manner. All right. So if the shear would cause a clockwise rotation, it would be considered positive. All right. All right, and then the last one would be for a couple moments. So if you had a rigid body like this, all right, we took our section cut in the center. What we end up getting is you'd have two moments. So this would be our external moments. All right, and then at our section cut, we have to have two moments in order to balance this out. All right, and in both of these cases, both of these two sections, what we'd end up getting is if we let these two moments act, what they would do is if the material was a little bit compliant, it would cause the materials to bend inwards in and this is like a concave up situation. Alright, so they would cause the materials to bend in a concave up shape, and then that's what we would consider to be considered a positive moment. Alright, so that is all of our notation. All of our notations are conventions for positive and positive, negative, shear, normal, and moments for internal forces. All right. So to determine our internal forces, we need to follow the following analysis procedure. So again, our goal is to determine the internal load. We want to determine the internal forces at a specific point. All right, in a member. All right, so our supporting reactions. All right, so first thing we need to do is we need to determine our support reactions. So we will use our equilibrium equations to determine our supports. Alright, this is not always required, but in many problems it helps if you know what the supporting reaction forces are. So the second step is to draw the free body diagram of your structure. So you want to make sure you draw all the external reaction forces acting on the free body. Alright, after you do that, you're going to make your section cut. point of interest. Alright, and then you're going to draw the free body diagram of your section cut of the cut section with the least number of applied forces. And you're going to draw all the internal forces. To be solved for. Alright, and then the last thing you're going to do is you're going to use the equilibrium equations. So you're going to find your resultant force, which is the sum of all the forces on the system. You're going to set that equal to the 0, and then you're going to find your resultant moment about a point, which is just the sum of all your moments about that point plus the sum of any couple moments applied to the system. Alright, and set that equal to 0. And you use these two equations to solve for your internal forces and moments. So your shear force, your normal force, and your moments. So that's the procedure for how you can determine the internal forces within a structure. And that concludes this video.